All right, so the goal for today is we're going to understand how to draw energy band diagrams for an NMOS device at various modes of operation. So last time in class, remember, we ended up with this slide here talking about how to calculate MOSFET currents. And before that, we were just looking at a qualitative description of what happens in a MOSFET during inversion. So we showed that when you put a positive voltage on the gate, you get an electric field. The electric field pushes away the holes. It pulls in the electrons, and that changes the material between the source and drain from P-type to N-type, and that forms a conductive channel between the two. So we're going to understand this phenomena and other phenomena in terms of energy band diagrams today. So remember, in this class, I want you to have an understanding of the physical interpretation of what is happening and also the energy band interpretation of what is happening. So today we're going to focus on the energy band interpretation. All right, so we're going to draw energy band diagrams for the NMOS device at various modes of operation, just like we did. We drew energy band diagrams for the diode in forward and reverse bias and at equilibrium. So we're going to start off by drawing the energy band diagram at equilibrium. So one key point here is that we are drawing the energy band diagram in the vertical cross-section, meaning we're going from the gate, from the metal to the gate oxide and into the substrate. In the PN junction, we were drawing the energy band diagram going from the P-type material to the N-type material. Here, we're drawing the energy band diagram going in this direction, from the metal to the gate oxide to the channel underneath it. So notice that we've drawn the metal here, this is the oxide, and this is the channel right underneath the oxide. Yeah. So this is a P-type semiconductor, the oxide is an insulator, and then the metal is metal. So the first step we do is we draw the Fermi level. And remember the rule that at equilibrium, no discontinuity or slope can appear in the Fermi level. So we draw the Fermi level as a horizontal line. So that's step one. So I have the Fermi level going across here. Now notice in the middle here for the oxide layer, we've talked about how to create energy band diagrams for metals and for semiconductors. Now we can also draw energy band diagrams for oxides, for insulators. So in the insulator, we actually don't even bother drawing the Fermi level because remember that the insulator really is non-conductive under most circumstances. Okay, so that's why we're leaving out the Fermi level in the oxide. So step two, we can draw the metal on the left. The metal only has E0 and EF. So you already know how to draw the Fermi level or the energy band diagram for metal. So the EF and E0 is separated by this phi m, the metal work function. Does anyone remember what E0 is from our discussion on metal semiconductor junctions? What is the definition of it and what does it represent? It's the free electron level. That's correct. And what is the free electron level? Yeah. When the electron has attained enough energy to get to the free electron level, it is free from the lattice. It's freed from the atomic structure. It's attained nirvana. So the second part is here we draw the oxide. The oxide only has E0. We don't put the Fermi level in there because there are no carriers in the oxide. So we can just draw the oxide as a diagram like this. The oxide does have a free electron level because if you blast even an insulator with enough light, you can cause electrons to be ejected from that material. Step 4, we draw the P-type semiconductor on the right. So this is for an NMOS device, right? For an NMOS device, the substrate is P-type. So we already know how to draw a P-type semiconductor. We position EC, EV, and then the intrinsic level EI, depending on the doping and the band gap. So the Fermi level is fixed. We draw these three bands around it. We also draw E0. Okay? So the position of EC, EI, and EV will depend on the doping. The doping determines this distance, the distance between EF and EI. All right, you already know how to calculate that distance based on the doping. We can also add E0 to the diagram because we know the electron affinity, and we know the spacing between EC and E0 in the semiconductor. Now the way that I've drawn the diagram here represents the case where phi m is equal to phi s. This is not necessarily the case with most metals and semiconductors. In fact, most often it isn't. Okay, I've only drawn it like this for simplification purposes. In most cases, phi m and phi s will be different. Okay, which will result in some band bending. We'll get into that a little bit later. All right, so the last step is that we connect E0 together like this. And in this case, E0 appears as a flat line, just as the Fermi level appears as a flat line. If phi m is not equal to phi s, there's going to be some bending in the E0 levels. There's also going to be some bending in EC, EI, and EV, just like we saw with the metal semiconductor junctions. All right, so this is what the band diagram looks like. We can analyze the band diagram. Okay, this is a p-type semiconductor. In a p-type semiconductor, we're interested in what the holes are doing. So we can see that there are a bunch of holes here. Oh, sorry, this is the electron affinity there. We can see that there are holes in the valence band for a p-type semiconductor, and those holes see this barrier here. Okay, that's the oxide. So the holes are really not going this direction, they're not going in this direction. The system is at equilibrium. Now, I'm put these red arrows here just to illustrate the fact that the holes cannot go through this barrier. You know, just like in the semiconductor, the holes can't go through the oxide layer. They can't go through the insulating layer, right? So this is physically being what's represented in the energy band diagram. So this is the same diagram from the book, if this is more helpful to see. This doesn't really present any new information per se. One little shortcut that's shown in the book here is that these little zigzag lines represent the fact that there's a large distance between E0 and EC here, right? Because when we draw this diagram, we're not drawing everything to scale. We know that the band gap of silicon is 1.12 electron volts. But electron affinity is around 4 electron volts. Okay, so we're really not drawing these things to scale. This thing in the book is just making sure that you understand that there's a much larger gap here than there is here. Phi m and phi s are the modified work functions. These are the things we talked about when discussing metal semiconductor junctions. We'll also introduce this term here, Q phi f. This is just the distance between EI and EF. Okay. Now, phi f is given in terms of volts, whereas whenever I tell you to find the distance, the separation between EI and EF, I tell you to find it in electron volts. But this distance in electron volts is Q times phi f. So the units for phi f is actually going to be in volts. All right. Next is the NMOS device at accumulation. Now, I'm going to draw, I'm going to draw the NMOS device in accumulation mode. Let's see here. We've talked about inversion mode. Let's talk about accumulation mode. And I would like you to figure this out, because I think this is a good exercise. Suppose we have an NMOS device, so a p-type substrate, and then you have the source, and you have the drain up here, the gate in the middle. what will happen if we apply negative voltage to the gate? What if we apply negative VGS? What kind of charges are we going to build up on the gate? Well, in this region, so if we apply, suppose we apply a negative voltage here, we're going to end up building negative, we're going to have negative charge buildup on the metal. Which way is the electric field going to point? Right, the electric field will point up instead of down. This is just the opposite of inversion. So in accumulation mode, we're putting a negative voltage on the gate. The electric field is pointing up, so what is that going to do to the holes and electrons in the substrate? Sorry, this is N-type, forgot to add that. So we have holes and electrons in the substrate. What's going to happen to the holes? Yeah, the holes are going to accumulate here. So the holes will go up like this. And what about the electrons? They're going to be moved away. Right. So what we'll end up with is a lot of holes accumulated here. All right. So this is N-type. The drain is N-type, and in the middle here we have a bunch of holes that have accumulated there. Do we have a conductive channel? No, because it's going from, looking across, it's going from N-type to P-type to N-type. All right. So you're accumulating holes here. So let's now look at accumulation from an energy band diagram perspective. So an accumulation mode refers to the accumulation of majority carriers under the gate. In other words, the accumulation of holes under the gate for an NMOS device. In an NMOS device, accumulation mode is achieved by applying a negative voltage to the gate. All right. Now, I just showed you the physical model of that. Now we're going to draw the energy band model. So the rule is, if you apply a negative voltage to one side of the energy band diagram, that side, that Fermi level, is higher with respect to the other side. So this is the equilibrium band diagram showing that the Fermi levels are the same. So if we apply a negative voltage to the metal, then the left side of the band diagram goes up relative to the right side. So if you can imagine moving this entire section down like this, right? So you have to think about everything here moving as a stack. So I'll show you again. This entire thing has to move as together because the distance between EC and EV has to stay the same. The distance between EC and EI has to stay the same. All these distances between these different levels have to stay the same. So it moves as a unit. Okay, we applied a negative voltage on the metal. So the metal now has a higher Fermi level than this side. The difference between the Fermi level, the difference between here and here, the gap between these, is exactly the voltage that you applied to the system, exactly the negative voltage that you applied. Now, it's not enough to just shift this band diagram down. We also have to connect the bands now. So we have to connect E0, and this causes a bending of E0. Okay, just like we saw with the metal semiconductor junctions. And we'll see that EC, EI, and EF, and EV, they also bend in the same direction. So which direction is E0 going to bend? It's going to bend up. It's going to curl up like this. Okay, so E0 goes up like this, and so do the other bands. Okay, just to show you again, E0 curls up, and so do these other bands, because the distances between those levels all have to remain the same. So this is how you would go about drawing the energy band diagram. Now we have to analyze the energy band diagram. Again, since we have a p-type substrate, we're interested in what the holes are doing in that substrate. The number of holes in a semiconductor is determined by how close EF is to EV. Let's recall this concept from Chapter 3. If you move EF closer to the valence band, what happens to the hole concentration? Well, let me rephrase the question. What happens when we increase the doping of a semiconductor? Which direction does the Fermi level move?
P-type doping?
In a p-type semiconductor, yeah. It moves towards the valence band. That's right. When you increase the doping, when you increase the carrier concentration, the Fermi level moves towards the valence band. If we're talking about a p-type semiconductor. So the closer the Fermi level is to the valence band, the more holes you have. So let's look at this diagram here. Out here, the Fermi level is some distance away from the valence band. So we do have a p-type semiconductor here. What will the hole concentration be here, where the valence band curls up like this? It's going to be higher, right? The closer the Fermi level is to the valence band, the more holes you have in the semiconductor. So just by drawing this energy band diagram, we can actually start to understand what the holes are doing. Whenever we have a slope in the energy band diagram, what does that tell us? We're getting close. There's a potential difference, yes. There's a slope in the band diagram means that there's an electric field. Right? So you remember how in this diagram we were just showing that there's an electric field pointing up? That electric field is represented by the fact that there's a slope in the band diagram here. All right, so now the holes that are in the semiconductor, as they move this way, they actually start to accumulate in this region here. So there's a higher concentration of holes right at the interface between the semiconductor and the oxide. So this thing that we drew up here, the accumulation of holes near the gate, this is the physical model, is represented by these holes that are accumulating here in this region. The fact that there's a slope here represents that there's an electric field. The holes, remember, electrons like to go down the slope, holes like to go up the slope. So holes will drift into this region. And this region is called a potential well. The holes go there and they basically get stuck there. This is called a potential well. You can also have potential wells for electrons. All right, so this is the accumulation mode. Any questions about this? Make sure that you're comfortable drawing these types of band diagrams on your own. There are always questions on band diagrams on the exam.
What is the purpose of to make the potential?
Oh, what is the purpose of a MOSFET operating in this mode?
Yep.
So MOSFETs at accumulation can act as capacitors, can be used as capacitors. So this is one use of them. Obviously, the device is not on in the accumulation mode. Right. The reason we're going over the accumulation mode is just so you have a complete understanding of what happens in a MOSFET, whether you apply positive or negative potential. But yeah, the device is still off at accumulation mode. This is a diagram from the book. Same idea here. You can see the accumulation of holes near the oxide layer. The difference in the Fermi levels, this is the Fermi level in the metal, this is the Fermi level in the semiconductor. The difference between them is given by QV. And V is the applied potential to the gate. So if a negative bias is applied, the semiconductor band bends downward. Well, it curls upwards, but this side of the diagram goes down. NMOS at depletion. All right, depletion mode happens when we apply a small positive voltage at the gate. So if we move over here and we just draw the depletion mode, I wonder if I could just copy this. I think there's a way. Yeah. Let's see. I think there's a way to copy this. Yes. Great. Saving myself work. Okay. So in depletion mode, we're applying a small positive gate voltage. Okay, when we apply small positive gate voltage, we accumulate some positive charges here, and there's an electric field pointing down, but the electric field is relatively weak. Now, in the depletion mode, what we are doing is we are depleting this region. The holes, the majority holes, are being pushed away from the channel region underneath the gate. But the electric field is not strong enough to pull in the negatively charged electrons yet. Okay, it's just strong enough to push away the holes. So if you have a p-type semiconductor and you remove all the holes, what are you left with? Yeah? Remember with p-n junctions, what happens when the holes left the p side and traveled over to the n side? It left the negatively charged ions. What was that called when you leave behind the negatively charged ions? It's called the depletion region, right? That area is depleted of the majority carriers, and what you're left with is those immobile ions. So we can draw in those immobile ions like this. These are not electrons, mind you. They're not electrons. They're the negatively charged ions. All right. So in the case of a p-type semiconductor, it would be like boron atoms. Is this conductive? Do we have a conductive channel between the source and the drain? We don't. That's correct. We do not. Even though the channel here is negatively charged, these are immobile charges. These charges cannot move. So it's not a conductive material. It's not an n-type material. The only way to make it an n-type material is to bring in the electrons from the substrate, bring in those minority electrons. So at this point, this is what happens when you apply a small gate voltage, not enough to invert the channel. When the holes leave, they leave behind a depletion region. But this is not an n-type material. It's a depletion region. So we're going to now look at that in terms of the energy band diagram. So the NMOS in an NMOS depletion mode is achieved by applying a small positive voltage to the gate, and as we talked about, the holes leave the gate. From the energy band diagram perspective, if you apply a positive voltage on the metal, the right side of the diagram goes up. The right side of the band diagram goes up relative to the left side. This should say left. So let me fix that. Okay, so the right side of the band diagram will shift up as a unit. You can see here, right? The whole stack moved up. And then you have to connect the bands. When you connect the bands, this is what it looks like. This curves down. All right. Oh, shoot. Okay, let's do that again. Moves up. All right, then you have to connect these bands together. And you end up with a band diagram that looks something like this. Okay, now we have to analyze the band diagram. P-type semiconductor. All right, so we're interested in what the holes are doing here. Oops. So the holes are being pushed away from this region here. And how can we tell that? Well, whenever there's a slope in the band diagram, there's an electric field. Holes move in the same direction as the electric field. If there's a positive slope, that means there's a positive electric field. The other way we think about it, as I said before, holes like to go up the slope. Electrons will go down the slope. So the holes are would go up the slope this way, and they move out. So in this region, what you're left with is a depletion region. Now, one way we know that is, first of all, there's a slope in the field, so there's an electric field in the depletion region. The other way we know that is by looking at the location of the Fermi level with respect to the other three bands. In this case, the Fermi level out here is relatively close to the valence band. So this is definitely a p-type semiconductor. What is it at the interface? Look at the location of the Fermi level with respect to EI, EV, and EC. Exactly. It becomes more like an intrinsic semiconductor. So it doesn't have a high hole concentration. It doesn't have a high electron concentration. So this semiconductor starts to behave sort of like an undoped semiconductor. This is the depletion region, by the way. There isn't a high hole concentration. There isn't a high electron concentration. There's an electric field represented by the slope here. Any questions on the depletion mode? Same diagram from the book. All right, now the device at inversion. Inversion we've already talked about, but I'll just add it here. All right, so inversion. So inversion we already understand very well. I'm just adding it just for the sake of completeness. We apply a large VG here, right? Something that's greater than the threshold voltage. So VG is greater than VT. So we accumulate a lot of positive charge here. We have a very strong electric field which drives away the holes, and it pulls in the electrons. All right, so this is the concept that we've already talked about. So I just want to point out that these electrons, there's two types of negative charge carriers in the channel during inversion. All right, there are these guys. This is the immobile negative ions. This is what forms a depletion region. So there's some negative charge there. And there's also these mobile electrons, the minority carriers from the substrate, which accumulate. They accumulate right at the surface here. Okay, they're not in the oxide, but they're right at the surface here. I'll show this more on a slide, on a subsequent slide. Okay, so there's two types of negative charges in the gate. There's the mobile electrons and the immobile ions. Is this channel conductive? Yes. The mobile electrons are making it N-type. And now you have a conductive channel, conductive N-type channel, connecting the source to the drain. So looking at inversion now in terms of the energy band diagram. Inversion mode refers to the accumulation of minority carriers under the gate. In an NMOS, depletion mode is achieved by applying a large positive voltage to the gate. The gate voltage is greater than the threshold voltage. We're going to figure out how to calculate the threshold voltage later. For now, just draw the energy band diagram. If you apply positive voltage on the metal side, EF on the right side of the diagram goes up relative to the left. Let's make this correction again on the notes. And again, we see band bending. So it's really the same situation as the previous slide, except there's more bending in the band. So this moves up more than it did last time. Now again, we do the band bending. We connect E0. We also can bend EC, EI, and EV by the same amount. Now in this case, notice where the Fermi level is. Just looks like the... Okay. again. Yeah, it's not, for whatever reason, it's... All right, the Fermi level goes like this. So what does this mean? What does this mean in terms of carrier concentration? Out here, the Fermi level is close to the valence band, so it's p-type. And Hunte, you were saying? Yeah, at the interface it becomes n-type, because out here, the Fermi level is now closer to the conduction band. Right? So you see this band bending actually converted the material from p-type to n-type at the interface. It's p-type out here, but at the interface is now n-type. So since it's n-type, what happens is that electrons, when the Fermi level is close to the conduction band, that means we have electron concentration. So we have a large electron concentration just right at the interface. But out here, since the Fermi level is far away from the conduction band, we don't have very many electrons. Out here we have holes. And those holes, as we saw earlier, the holes in the substrate got pushed away because holes like to go up the slope, so they got depleted in this region, so the holes moved away. The electrons accumulate in this region here. This is also called the potential well. The electrons are collecting inside the potential well. This is called inversion because we've effectively switched the material at the interface from p-type to n-type. And you can see that there's a strong electric field right at the interface. So any questions on the energy band diagram for inversion? Okay. Same diagram from the book. So the result is the accumulation of minority electrons near the oxide. The best way to do these types of problems is just to practice. Practice drawing out the band diagrams at accumulation, inversion, and equilibrium. So the NMOS device at strong inversion. We now have to understand how much bending we need in order to achieve inversion. Okay, the descriptions that we've been giving thus far are qualitative. Right now we have to get quantitative because we want to actually calculate what the threshold voltage is. Right, the threshold voltage is the voltage that you need to apply to the gate in order to get a channel to form. So you guys have talked about the values of threshold voltage in Electronics 1. In this class, we're going to talk about how to derive the threshold voltage. And so the first thing we have to do here is define what strong inversion is. The strong inversion is, the voltage that's required to put the MOSFET into strong inversion, that is the threshold voltage. So how much inversion do we need to have what's called strong inversion? That's what this diagram here is showing. If a large bias voltage is applied, we are in the strong inversion state. In the strong inversion state, the inversion channel has accumulated enough electrons in order to efficiently conduct electricity. The way that we define strong inversion is when the concentration of electrons in the inversion channel is the same as the whole concentration in the p-type substrate. So as an example, let's say your MOSFET has a substrate doping of 10 to the 16th. So what is the whole concentration there? What's the whole concentration in the substrate? Yes? The substrate doping is 10 to the 16th. So what's the whole concentration? It's the same as the doping levels. Does this sound familiar to everyone? Whatever, if you're doping at 10 to the 16th, then the whole concentration is 10 to the 16th, right? That wasn't a trick question. I think some of you thought it was a trick question. So we define strong inversion as the voltage required to create an electron concentration of 10 to the 16th at the inversion region. Okay. So the electron concentration at the interface should be the same as the hole concentration away from the interface. That's what strong inversion is defined to be. If your substrate doping is 10 to the 17th, then you need to look at the voltage that's required to make the electron concentration 10 to the 17th at the interface. From the perspective of the energy band diagram, this definition that I just gave you will happen when the bending in the diagram, Q phi s, is equal to 2 times Q phi f. This is a little confusing. They use phi s here in this figure. This does not refer to the semiconductor work function. Okay, phi s, let's assume that phi s is the semiconductor work function. This distance here, this is equal to 2 phi f. This is the amount of bending that you need. Don't get this confused with the semiconductor work function. In fact, if you want to call this something else rather than phi s, I would suggest doing that. So when the amount of bending is equal to twice the distance between EI and EF, that's when strong inversion occurs. So, sort of qualitatively speaking, it means when EI has bent down so that it's below EF, and these two distances that I'm pointing out, this distance here and this distance here, are equal to each other. It doesn't show that way in the diagram. This is not drawn to scale, but this distance here and this distance here should be equal to each other. So the amount of bending is equal to 2 times phi f. All right, now we're going to start deriving the threshold voltage. So there are a lot of different there's a lot of different things that we need to calculate, and a lot of different concepts that come into play here. So I'm summarizing all of those in this slide to help you better understand. So the diagram is showing the charge distributions and electric fields of an enhancement mode NMOS device at strong inversion. The source and drain regions are not shown. In other words, we're focusing in. What's happening with this? Try this again. In other words, we're focusing in on just this region here. We're ignoring the source and the drain region. So this portion here we're focusing in on. So we have the metal up here, then we have the oxide, and then we have the semiconductor substrate down here. We're going to look at each one of these parts one by one. So you remember how we did this full electrostatic analysis of the p-n junction? We looked at the depletion region, we looked at the charge buildup in the p and the n sides, we figured out the electric fields and all that good stuff. We're going to do the same type of analysis for the NMOS device at inversion. I would say this is a little bit more complicated. But having understood how diodes work, I think you can start to understand how these work as well. So, first of all, the metal here, remember the metal gate has properties phi m, the metal work function. The oxide, the properties related to the oxide is the thickness of the oxide. That's the actual physical thickness. That's usually given in terms of nanometers, and you have to convert that to centimeters when you do your calculations. The properties of the oxide include the dielectric constant of the oxide. All right, for silicon dioxide, which is a common dielectric, a common oxide that's used in MOSFETs, epsilon r is equal to 3.8. So in order to find the dielectric constant epsilon is equal to the relative dielectric constant epsilon 0 times the relative dielectric constant epsilon r times the dielectric permittivity of vacuum, epsilon 0. Epsilon 0 is 8.85 times 10 to the negative 14 farads per centimeter. Epsilon r for oxide is 3.8. So this is what you've done in your homeworks. Going to the semiconductor, the properties of the semiconductor, it includes the substrate doping, and there's also the semiconductor work function, phi f, that's the distance between EI and EF. There's the band gap EG, and there's also the dielectric constant of silicon, and that is 11. Okay. A few other things. Let's define phi f. Okay, I just mentioned phi f. Phi f is the distance between EF and EI in the substrate. And as you know before, this is just equal to KT over Q ln of NA over NI. So we've done these types of calculations before. But keep in mind that when you calculate this, this will give you a formula in terms of volts, not electron volts. The formulas that you were using previously is just KT ln of NA over NI. This formula is KT over Q ln of NA over NI. So you're going to get a quantity equal to something volts, 0.6 volts, 0.7 volts. So this is the semiconductor doping factor, phi f. The semiconductor work function is also given in volts. Sometimes I actually see the semiconductor work function given in volts or electron volts, so it'd be a little bit confusing sometimes, but I'll make sure that I clarify it in any of the questions that I give you. So the semiconductor work function is phi s. The depletion width, now getting to these last two parts here, these are critical in calculating the threshold voltage of a MOSFET. So now looking at this diagram, okay, we have positive charges at the metal gate. We mentioned that before because we placed a positive VGS. So there's a positive charge buildup here. The positive charge buildup results in a negative electric field, or the electric field which is pointing down. And that electric field exists through the oxide, and that it also exists through a portion of this region as well. As a result of the electric field, the electrons like to go opposite the electric field, so the electrons accumulate near the interface. This is the inversion channel, shown in blue. And below that, we have the depletion region. Okay, again, just to relate it to this diagram, remember I said that the electrons accumulate just near the surface here, but the depletion region actually extends out a little bit further. So this is the width of the depletion region. It's given by WD. And the formula for the depletion width is 2 times the square root of epsilon times phi f divided by Q times the substrate doping. All right, this can be derived. We're not going to go into the derivation of it, though. Okay. Just know that this scales as phi f, so it scales as the doping. And then this is also a doping term. Right? So you can think about how the depletion width scales as doping. You can see that it's very similar compared to a PN junction. What happens in a PN junction if you increase the doping? What happens to the width of the depletion region?
Decreases.
It decreases. That's correct. The same thing happens in a MOSFET. If you increase the doping of the substrate, you decrease the width of the depletion region. Yes?
The width itself is constant, right? It's just the side that was doped that gets smaller.
The width is constant?
The width of the depletion region constant, and then the side that's doped or the doping's increased gets smaller, right? It's a ratio, right? So I mean,
I didn't quite understand the question.
The actual depletion region width stays the same, and the side that's doped gets smaller. Do I understand right? Or does the width itself change?
So do you mean this dimension here, the depletion width?
Mm-hmm. Outside, yes, it's smaller.
So this depletion region width is dependent on the doping. But I mean, you're saying does it stay the same?
The width altogether, I'm referring to the PN junction because you were saying the width stays the same. But the width decreases, but it's just the side that's doped that decreases. Right? And then the other side increases.
In a PN junction, the depletion width depends on the doping,
Right,
but it also depends on the applied voltage,
yes.
if that's what you're talking about. When you forward bias a diode, the depletion width actually gets narrower. And when you put in reverse bias, the depletion width actually increases. Now in the case of the MOSFET, you can see that it's dependent on phi f and the doping here. So this formula states that it's actually independent of the applied voltage. So you have a depletion width here. These orange ions represent immobile charges. Okay, these are not responsible for any type of electricity conduction. All the electricity conduction, the conductive channel is right up here, which is called QS, the surface charge. QM is referred to as a metal charge. QD is referred to as the depletion charge, and that's given in coulombs per centimeter squared. For an NMOS device, the depletion charge is negative Q times NA times the width of the depletion region. The width of the depletion region is given in centimeters, so it's just this distance here. Okay, so this is centimeters. NA, the units for NA is 1 over centimeter cubed. And this is the units for Q is coulombs. So the depletion charge is given in terms of coulombs per centimeter cubed. And for a PMOS device, it's the same formula, except you have ND here instead of NA. And for a PMOS device, the depletion charge is positive, not negative. So all these things that we're deriving for an NMOS device, I would like you to go through on your own and draw a similar diagram for a PMOS device. It's probably the best way to study and understand these concepts. If you could draw the similar diagram for a PMOS device, you'll be in very good shape. So any questions about this diagram? All right. Let's see if we can... Let's do one more slide, and then we'll take a short break and do the presentations. So the NMOS device at inversion. So we talked about the energy band model of it, with the strong the energy band model of the NMOS device at inversion. We defined what strong inversion is, and we looked at some of the what the charge distributions are at inversion. Now this slide is sort of talking about the physical interpretation of the NMOS at inversion, and it's looking at electric field and also electrostatic potential and charge. Now, remember for a p-n junction what we did when we were deriving the electrostatic potential for a p-n junction, we said, okay, we know what the charge density is. Let me just draw this out and remind you. For a p-n junction, we did this type of analysis, electrostatic analysis. We said, well, there's negative charge buildup here, positive charge buildup here, and so we went through. First thing we did was we drew a charge density plot. The charge density plot looks something like this. This is X. This is the charge density. Then we drew the electric field plot. The electric field plot looks something like this. And then we drew the electrostatic potential. You guys remember this analysis that we did for diodes? What was the relationship between charge and electric field? What did we have to do to go from charge to electric field? We had to integrate, that's correct. And to get to electrostatic potential from electric field, we also had to integrate. But we started off with the charge density. Right, and the charge density we got an understanding by looking at the properties of the depletion region. We said that a few important concepts, that the charge neutrality concept, the amount of negative charge has to equal the amount of positive charge. These two areas, the total charge in the total charge here had to equal the amount of positive charge here. So just to remind you what we did with p-n junctions. Now we're doing a similar thing for MOSFETs. We start off with the electric field. We start off with the charge density. From the charge density you can figure out the electric field, and from the electric field you can then figure out the electrostatic potential. Now the reason we're interested in the electrostatic potential is because it helps us derive the threshold voltage. When we were talking about diodes, we were very interested in the electrostatic potentials because that's what told us what the diode voltage was, that 0.6, 0.7 volt number. right? For MOSFETs, the reason why we do this electrostatic analysis is to help us derive the threshold voltage, the gate voltage that is needed to put the channel in strong inversion. In other words, to turn the device on. So this is what the charge distribution looks like. I've shown it schematically in this diagram. Positive charge buildup here, negative charge buildup under the gate, more negative charges as part of the depletion region. So this is shown, graphing it as a plot. So this is the metal here. This is the oxide in the middle here. And then this is a semiconductor on the right here. So x equals 0 is the interface between the oxide and the semiconductor. So here, there's you can see the charge density is 0 here, and all of a sudden the charge density goes up like this. This is all the positive charges in the metal. So that's this thing here. There's a high charge density right at the metal interface. In the oxide, there are no charges. So the charge density there is 0. Once we get down here, there's a bunch of negative charges. There's a high concentration of mobile electrons. We call that the surface charge. And then there's a lower density of electrons due to what's called the depletion charge. So this inversion channel, it should be QS, okay, the surface charge here. So that there's a high concentration of electrons here due to the inversion channel, and then the depletion charge is a little bit less charge density there, but still you have the negative charge density. So this portion here is referring to these orange charges, depletion charge here. These are both negative charges. So the charge distribution in a MOSFET, it looks a little bit different than a PN junction, but hopefully you can understand it. This is given in a charge density, charge per unit area. To go from here to the electric field, you have to integrate this plot going from left to right. So the electric field is one over epsilon, the integral from negative infinity to x, rho of x dx. I think my battery's starting to die here. So if we were to state this in words, the electric field at point x is the integral, or the area under the curve of everything to the left of x. Right, so this is the mathematical definition of the electric field, and this is sort of like the more intuitive understanding of what the electric field is. It's the area under the curve of everything to the left of point x. So if we're, if our point x is here, the integral of everything to the left of it is obviously 0. There's nothing here. Once we get to here, now we're talking about we have to include this area here, the area under the curve here. So notice that the electric field starts at this point and then it goes up, right? And so it stays constant here. As we go from this point to this point, the electric field is not increasing because we don't have any additional charges here, no additional area to add up. So the electric field jumps very quickly up here and then it stays constant through the oxide. So what we're talking about here is the electric field within the oxide. Now the electric field drops it drops suddenly because, if we're integrating everything from some point x, everything to the left of it, first we had all this positive area, and now we have all this negative area that's also included. So if we're here, let's say, right where my mouse clicker is, we have this area here, and then we also have some negative area that we have to include. The sum of those things is going to bring the total electric field down from this high value. It's going to start bringing it lower. As we continue from this way all the way to here, the depletion charge is also going to bring down the electric field further until it gets to 0 by the time we get to the edge of the depletion region. So there's electric field in the oxide. The strongest electric field exists in the oxide. There's also an electric field in this region too. And by the time we get out of the depletion region, out down here, the electric field is now 0 again. Based on this electrostatic analysis, it is possible to calculate the width of the junction, so the distance between here to here, the width of the depletion region, according to this formula here. 2 times the square root of epsilon phi f over QNA. That's basically the same thing as this thing here. Now, if we want to find the electrostatic potential is the integral of the electric field. So phi is the integral of E of x. Integral from negative infinity to x. Same idea. So as we integrate from left to right, we accumulate this area here. This increases the electrostatic potential, and as we start going from left to right here, wait a minute, it's the negative. Yeah, this part's a little bit confusing. So this is the formula we have to use. If we want to figure out the electrostatic potential from the electric field plot, it would actually start going down like this, and it would become negative like this as we go here. Now I want to compare that to this diagram that you see here. It's the same shape. If we figure it out mathematically according to this formula, you'd start at 0, and then this would just become negative as you go further and further down, as you start accumulating the areas here for this representing the electric field. But what they do instead is in this graph is that they take this entire relationship and they shift that entire plot up. They shift this up so that you get a plot that looks more like this. Okay, they're basically changing the 0 voltage to the right side of the diagram instead of the 0 voltage being the left side of the diagram, which is the way, if you were to do it just mathematically, this is the relationship that you'd get for V of x. Oops. So when you integrate this function, you get a function that looks like this. This is the voltage everywhere in, this is the voltage in the metal. Okay, remember, there's a large voltage that's applied to the gate side of it. So this is your applied voltage. Some of that voltage drop occurs over the oxide. A little bit of that voltage drop occurs over the depletion region. And then this right side of the diagram is 0 voltage here. All right, so when you apply a VGS to your MOSFET, some of that VGS drops over the gate oxide, and some of it drops over the semiconductor depletion region. And the amount that drops over the semiconductor depletion region causes that band bending that we talked about on the previous slide. So if we want to turn on the device, we have to apply a large enough voltage so that the potential drop across the semiconductor is enough to bend the band so that we get an inversion channel. So after break, we'll start talking about how to calculate the threshold voltage. Okay, so conceptually, you know what it is now. You need to apply a large enough voltage. You have to, if we want to calculate the threshold voltage, we have to account for a voltage drop over the oxide and enough voltage applied to bend the diagram, bend the semiconductor band diagram enough to get strong inversion. So we'll quantitatively describe that after the break. So let's take a 2-minute breather. Kamaljit, you can come up. Oh yeah. All right, so continuing talking about threshold voltages. So we know that in order to create a channel to make the MOSFET conduct, we have to have strong inversion. And so we just went through this electrostatic analysis of what strong inversion actually is. And so the gate voltage required for strong inversion is called the threshold voltage. And the MOSFET is considered to be on when VG is greater than VT. So these are the equations for the threshold voltage, and it considers the factors that each one of these 3 factors we'll consider in the next few slides. The threshold voltage is equal to the flat band voltage, which is normally negative, usually a negative number, plus the depletion charge term. And the depletion charge term is positive for an NMOS, it's negative for a PMOS device. And then the strong inversion term, this 2 phi f term, which has to do with the doping levels. And this is positive in an NMOS device, it's negative in a PMOS device. So we're going to go through each one of these terms to see how each one affects the threshold voltage and where it comes from. So the first term here is the NMOS at strong inversion. This is the slide that you saw before. So the first contribution of this term, this is equal to 2 phi f. This term represents the amount of bending we need in the band diagram in order to create this potential well for the electrons to go through, in order to invert the material from p-type to n-type. Okay, in the case of an NMOS. And for a PMOS device, it's switching from a p-type to an n-type. So this will be a negative quantity for a PMOS device. It'll be a positive quantity for an NMOS device. This term depends on the doping. Phi f is the difference between EI and EF. What happens to phi f as we increase the doping? Does it go up or does it go down? Yeah, if we're talking about an NMOS device with a p-type substrate, increasing the doping will move the Fermi level down. So it will increase phi f. In the case of a PMOS device, the Fermi level will be up here, and phi f is again the difference between EF and EI. Okay, so the magnitude of phi f will increase with doping, regardless if you have an NMOS or PMOS device. So this term is doping dependent. The second term is the depletion charge term. The charge stored in the depletion region contributes an electric field. This bends the band diagram and therefore has to be considered. All right. To calculate the effect on threshold voltage, recall that the MOS gate depletion region looks like a capacitor. There's positive charge and negative charge. And the voltage drop across the depletion capacitor is equal to V is equal to Q divided by C. So let's start to understand this conceptually. There's positive charge on this side, and then there's negative charge on this side. Okay. There's an electric field across the oxide. Now this looks very much like a capacitor, right? You're putting a positive voltage on one end, a negative voltage on the other end. You build a positive charge on the positive plate, a negative charge on the negative plate. The difference is that one side is metal. You still have a dielectric, but the other side is a semiconductor. There's some rules for a capacitor that still holds true. The number of positive charges here has to equal the number of negative charges here. So if we sum up all the positive charges on the metal gate, it will be equal to the number of negative charges in the surface plus the negative charges in the depletion region. But essentially, this is a capacitor. Whenever we want to calculate the voltage drop across a capacitor, you remember this basic equation, Q equals CV. So this is a fundamental relationship for a capacitor. Q is equal to CV. Q refers to the amount of charges, the number of charges. C is the capacitance, and V is the voltage. So the voltage is equal to Q divided by C. The voltage drop across a capacitor, for a resistor, you guys know V equals IR. For a capacitor, V is equal to Q over C, the voltage drop across a capacitor. Does anyone remember the formula for a parallel plate capacitor? C is equal to what? I'm sorry? Yep. It's epsilon A divided by D. All right, the area is sort of the area of the parallel plate capacitor like this. This is the area, and then the spacing between the plates is D. And epsilon is the dielectric constant of whatever is between the plates. All right, so getting back to this then, we're trying to find the voltage drop across the capacitor. So this voltage drop V is equal to Q divided by C. And this is what appears in this equation. This term represents the voltage drop across the capacitor. This term represents the voltage drop across the depletion region. All right. So the depletion voltage reduces the threshold voltage. The voltage is equal to QD divided by CI. QD is the depletion charge. All right, this is, remember the amount of depletion charge, that's this amount of charge right here. The amount of negative charge here is going to be equal to the amount of positive charge up here. So that's why we have, QD here, divided by CI. CI is the insulator capacitance. And this is given as in terms of an incremental capacitance. Instead of doing epsilon A over D, it's just given as epsilon over D. So this is a unit capacitance. It's given in farads per centimeter squared instead of just farads. All right, D is the thickness of the oxide. So this is what you calculated in your homework. Epsilon of the oxide divided by the thickness of the oxide. So the epsilon is going to be equal to the relative dielectric constant of the oxide, 3.8, multiplied by the vacuum dielectric constant, epsilon 0. Is 8.85 times 10 to the negative 14. So the depletion charge is equal to the QD divided by CI. How do you find QD? There is a formula for QD here. And you have to first find the depletion width, and then you can find the depletion charge. And yep, you know the depletion width is inversely proportional to the doping. And this term also includes the depletion, it includes the doping here as well. So the depletion charge will actually increase as a function of doping. All right, so the depletion charge is equal to QD over CI. The depletion charge will be negative. This QD will be negative in the case of an NMOS device, and it'll be positive in the case of a PMOS device. The third term is the flat band voltage. The flat band voltage is equal to phi m minus phi s minus qi over ci. Phi m minus phi s, FIM is the metal work function, phi s is the semiconductor work function. This is, we talked about these things when we were talking about metal semiconductor junctions. So often the metal and semiconductor work functions are not the same. Thus, with zero voltage applied, the band is already bent. So you remember how when we drew this diagram here, drawing the NMOS device at equilibrium. All right, when we first drew the metal, and then we drew the oxide, and we drew the semiconductor. I told you that we were making this assumption that phi m is equal to phi s. And what that does, that means at equilibrium, there's no band bending. If phi m is not equal to phi s, you're going to end up with situations where there's band bending even at equilibrium. So let's look at this example here. So this is an example of something that is at equilibrium. The Fermi levels, how do you know it's at equilibrium? The Fermi levels are a horizontal line. They're matched up with each other. In this case, phi m is less than phi s. Okay, because the differences between the two, you actually get band bending even at equilibrium. And in this case, the band is bending down, so this is causing the channel to accumulate electrons even at equilibrium. This is an example of a depletion mode device. A depletion mode device is a device that's on at 0 voltage. We talked about enhancement mode and depletion mode devices. I'll just bring up that slide real quick. So a depletion mode NMOS is where the threshold voltage is negative. That means even if you apply 0 volts to the gate, the device will still be on. So in this case, this is what we have. This is a depletion mode device. Even with 0 volts applied, we're at equilibrium, but we still have an inversion channel. So this device will be on, it'll be on all the time, unless we apply negative voltage to straighten out the band here. All right, so that's what's done here. So this device at equilibrium, there's a channel already, so the device is on. The only way we can turn the device off is to apply a negative voltage to the gate, and that will bring this side of the diagram down. So it brings this side of the diagram down, the bands flatten out, and now we have a device that's off again. So the flat band voltage is when the bands are completely straight like this. There's no curvature or bending in them. The flat band voltage is equal to phi m minus phi s, and there's also the second term here. So since we've talked about the importance of the difference in the work functions, let's now talk about the charge, the oxide charge. So another effect which contributes is trap charge in the gate oxide. This is due to unclean processes. Charges add electric fields and also bend the bands. So looking at the second diagram here, now in our previous diagrams we've always assumed that the metal has charge in it, but the oxide has no charge. That we assume that the oxide is perfectly clean. Now you've seen the clean room, you've gone through there, you've seen how we do wet etching, dry etching processes, we do photolithography, and there's a lot of steps in there where the semiconductor has to be rinsed with water. Now one of the challenges in early semiconductor fabrication, one of the reasons why it made it difficult, is that if you use impure water, water has ions in it, right? Positive and negative ions. Well, those ions can actually find their way into the oxide of the semiconductor. Right? Let's say you're depositing your oxide layer in the semiconductor, and then you decide to clean the wafer in water. If your water is not absolutely clean, if you're not using DI water, the charges in the water can actually get into the semiconductor. And that will mess up your semiconductor big time. So if you have positive charges in the gate, these are called trap charges. Whenever you have charge, it alters the electric field, right? Charge determines electric field determines electrostatic potential. This is one of the very challenging problems in fabrication, because if you had, if one day you had dirty water, well, that would change all the threshold voltages of your device. Huge problem. So that's why clean rooms use very, very pure deionized water to prevent this type of problem from happening. And that's why they prefer using dry etching over wet etching. So ideally, your trap charges will be equal to 0. But sometimes, you know, when with these processes, you can actually characterize roughly how much trap charge you have. So the trap charge adds this term to the threshold voltage equation, Qi. This is the amount of trap charge. It reduces the flat band voltage, and it reduces the threshold voltage. Qi over Ci. Ci is the capacitance of the oxide layer. That's the term that you calculated previously. So the smaller Ci is, the more significant the Qi term will be. All right, so this affects the flat band voltage as well. Now, we're almost out of time here. Let me just do these last two slides here. So these are the three terms in the threshold voltage equation. Okay, the flat band voltage, QD over CI. This is a depletion charge term, and this is the strong inversion term. Now, this phi m minus phi s applies if you have a metal gate. So you have some type of metal, and a gate metal, and then you have the semiconductor work function. In a lot of MOSFETs, instead of using metal, they use something called polysilicon. And this is a chart. If your device is made from a polysilicon gate, you use this chart to approximate what your phi ms term is for a given doping. Notice that you have doping on the x-axis, and on the y-axis you have the phi ms term. This is for N plus polysilicon and a p-type substrate. So this is for an NMOS device, and this black line is for an N-type substrate. So this is for a PMOS device. Again, blue line is the NMOS device, black line is a PMOS device. I would give you this chart if I wanted you to just look up the value of phi ms instead of calculating it directly. So there's two possibilities. I could either give you the value of phi m, and you could calculate the value of phi s and figure out phi ms that way, because you know how to calculate phi s. We did that in the metal semiconductor junction chapter. Or if I tell you that it's a polysilicon gate, then you can use this chart to look up what phi ms is. No calculations involved. You can see that phi ms is determined by the doping. In an NMOS device, the more you dope it, the phi ms term goes down, becomes lower. So this chart shows typical threshold voltages and shows you how it changes with doping. In general, for an NMOS device, increasing the doping will increase the threshold voltage because you're increasing the amount of band bending required to flip the device from p-type to n-type. Okay, and I would like you to think about this on your own, how changing the substrate doping would change each of the terms in this equation. What would it do to the depletion charge? What would it do to phi f? What would it do to the flat band voltage? These are the types of questions I've asked in previous exams. All right, so it increases for an n-channel device, and it becomes more negative for a PMOS device. And when we're talking about the threshold voltage for a PMOS device, the magnitude of the threshold voltage increases with substrate doping. It becomes more negative. So this is an example of calculating the threshold voltage. I want you to be able to do this type of problem for the exam. There will be a problem on the exam like this for sure. There is a homework problem that's very much like this, where I give you some parameters and I ask you to calculate the threshold voltage. It takes some time the first time you do it because there's a lot of calculations involved. But I have the homework, and then I guide you through how to do it. So go through that on your own and make sure that you can calculate the threshold voltage for an NMOS transistor or for a PMOS transistor. So we will end class there today. Went over a few minutes. And I'll see you all on Thursday.